Hello everyone and welcome. Today we are diving into the world of neural networks to talk about two of the earliest and the most fundamental activation functions, the sigmoid and the tanh. If you ever wondered how a neural network makes a decision, you are in the right place. Let's get started. So in this video we will discuss about the sigmoid and tanh, the early activation functions. I am Anj and now we are going to break down what these functions are, why they were so important and what their limitations are. Before we jump in, here's the quick lookup and what we will cover. We will start with an introduction to the sigmoid function and its key characteristics. Then we will do the same for the tanh function. After that, we will compare their advantages and disadvantages, look back at their historical importance, and finally, see why modern deep learning has often moved on to the other functions, its full journey from the past to the present of activation functions. Alright, let's kick things off with the sigmoid function. Imagine you have a neuron in a neural network. It receives a bunch of information and has to decide how much of the signal to pass on. The sigmoid function is one way it can make that decision. Its main job is to take any input value, whether it's huge positive number or a huge negative number, and squeeze it into a tiny range between 0 to 1. Because of this, the output of sigmoid function can be interrupted as a probability. For example, if you are building a model to detect if an email is spam or not, a sigmoid function in the final layer could output 0.9, meaning there is 90% probability that the email is spam. Visually, it creates a beautiful S-shaped curve, and most important, it introduces a non-linearity into our models, which is crucial concept we will touch on the next. So, what's make the sigmoid function special? Let's look at its main characteristics. First mentioned, its non-linearity function. This is super important because real world data is almost never simple enough to be described by a straight line. Non-linearity allows our neural networks to learn complex curve patterns in a data. Second, its monotonic functions. This is a fancy way of saying that as an input value increases, the output value will always increases or stay the same, but it will never decreases. It's smooth, predictable curve with no wide bump. Third, it's a differentiable everywhere. This is a bit technical, but it is a magic that allows our networks to learn. During training, we use a process called backpropagation, which is like a rolling a ball down a hill to find the lowest point for the work. The hill needs to be smooth because sigmoid differentiable. It provides a smoother curve, enable the gradient based learning. However, it has a major weakness, the vanishing gradient problem. If you look at the S curve, you will notice that when the input is very large or very small, the curve becomes almost flat. A flat curve means the gradient or the slope is almost zero. During training, this tiny gradient can make learning incredibly slow or even stop. It taught escapely in deep neural networks with many layers. It's like the learning signal just vanishing. Now let's talk about sigmoid close cousins, the tan function, which stand for hyperbolic tangent. Tan is also a S-shaped activation function but with a key difference. Instead of mapping the input to a range between 0 and 1 like sigmoid, tan map them to range between -1 and 1. This might seem like a small change, but it's a big deal. The output of the tan function is zero centered, meaning it's average around 0. This property actually helps the networks learn more efficiently during trainings, make tan often a better choice than sigmoid for hidden layers of neural networks. Then the characteristics of tanh. These characteristics are very similar to sigmoid but with some improvement. Like sigmoid, it's non-linear and differentiable everywhere, allowing it to learn complex pattern and using gradient based optimization. It's also monotonic function, always increases, but here's the cool part. Tan H has a stronger gradient near 0. Its slope is steeper around the origin compared to sigmoid. This means that for input that are closer to 0, the learning signal is stronger, which can help speed up the training process. Unfortunately, the sigmoid Tanh also suffers from the vanishing gradient problem. Let's see their advantages. The biggest advantages for both is that they introduce non-linearity, which is absolute essential for neural networks to learn anything complex. They are both smooth and differentiable, which is a key requirement for use backpropagation. The algorithm power almost is modern deep learning, and specifically for sigmoid its 0 to -1 output range make it natural choice for the final layer in binary classification task. Now let's discuss the drawbacks. As we discussed, both functions suffer from the vanishing gradient problem for deep neural networks. This can be training killers. A specific problem for Sigmoid is that its output is not zero centered. All its output are positive between 0 and 1. This can lead to less efficient training because it can cause the update to fade to always move in the same direction. Tanh solve this with its -1 to 0 range. Finally, both functions can saturate. This means that for very high or very low input values, their output saturates at the end of their range and the gradient becomes near zero. Thank you so much for watching this video.